Hello Physics. Our new chapter is about interference and diffraction, which is things we've already learned lots about, but we're going to add to that learning in this chapter. So there's a little demonstration I want to show you as we start our chapter. Here's our lab setup. As you can see, we have a laser, and that laser is shining over here on the screen, and right now it's making a single dot. That's what lasers do, and they do it well. But we're going to put in here a slit. This disc has many different slits on it, and I'm going to turn it towards the sun, and you can see, or the light, you can see all those slits, and that there's different sizes. In fact, there's a graduated one, and so forth. We're going to let the laser shine on some of those slits and see what that does. So we put the laser, and then the laser is shining here on some slits. And you'll see another image there, but that's just a reflection of the light from the laser there. But the main beam is being shown right here on two slits. And I'm going to take you to the screen. I want you to see what's on this screen. You'll see that there's lots of little dots. And all these dots are being formed by that slit. I'm going to take the slit away and show you that it goes right back to the dot. I'm going to put the slits back in place, and you can see that they're there. I'm also going to slide it, and you'll see that those slits get farther and farther apart. So if I make it come closer to the laser, those dots get farther and farther apart. So what's going on here? So on our chapter here, Interference and Diffraction, page 520, we're going to revisit some of the concepts we've already learned, and that is interference. You remember there's two flavors of interference. There is constructive interference and there is destructive interference. So you'll remember that constructive interference is where two waves go together, and when they add, they make a bigger wave. So on the bottom of your text, these two red waves are in phase. They both go up at the same time and they both go down at the same time. One is much bigger than the other. But when they're in this phase, the two of them add together and make one big wave. And that's what we call the resultant wave from those two being added together. In example B, we have the red wave going up and the little red wave going down. And this time they're subtracting from each other, and we get the purple wave being the resultant, which is smaller than the big one, and in this case a little bigger than the small one, but overall the energy has been reduced much more than it was in this wave up here. Well, how does that work with light? We've talked about it with sound and waves and things like this, but what about light? Well, first of all, we're going to talk about monochromatic light. Mono meaning one, chromatic, chrome, actually refers to the idea of color. And when we say monochromatic, that means one color. So if we can get one color of wave, why we have the same frequency, the same wavelength. You'll remember that we have an equation for light, and that equation is C equals lambda V. C being the speed of light, and the wavelength and the frequency are related to the color. So sometimes we say it's the wavelength is the color, but if you change the wavelength, you also change the frequency. So every color that you see has a different wavelength. And if they happen to have the same wavelength, why then they could be in phase. If two light colors come together and have different wavelengths, they will have some constructive interference at a moment, and they'll have destructive interference and get what we call beats, which you remember from chapters before. So when we have two waves that are the same wavelength, then they could possibly be in phase. In phase meaning like two people walking in step, both the left foot at the same time and the right foot at the same time, like somebody marching. Military marching. So they would be in phase. We could also have it so that when one's on the left foot, one's on the right foot, and one's going up, one's going down, or vice versa, and they would be 180 degrees out of phase. The result here would be a larger wave, and the result here would be no wave. Well, when they are when they are a phase difference of 0, then we say that that is in phase. If the phase difference is 180 degrees out from each other, we call that out of phase. Now, light or a wave that can have a constant so that the waves do not shift compared to each other. And if they're the same wavelength, there will be no shift between the crests and the troughs. And if we can shine two light sources, same wavelength, then we can have what we call coherence, when the phase difference between the two waves is constant and the waves do not shift relative to each other as time passes. This is when the waves are coherent. So, can I just get any two light bulbs to do that? No, because if I take another light bulb, two light bulbs that are, say that you're looking to light your room by or see by, first of all, there is multiple colors coming out of your typical light bulb. And so you have lots of different wavelengths being emitted, and lots of them at different times and different directions. And so the light comes from random light bulbs we call incoherent. Light coming from the sun is incoherent. We use the same same word when we mean that when someone's talking and you can't understand them, we say that what they're saying was incoherent. We couldn't understand it. It doesn't have any patterns to it. So the only way that we can really get coherent light is lasers. And so that's why we started with the laser, because there's some pretty cool things we can do with lasers and coherent light. Okay, so let's talk about what some of the cool things are that we can do with this interference pattern from coherent light or light that's in phase. You'll remember from our ripple tank experiments and so forth that if we create a wave, it keeps on going straight towards where it started. But if we go to a barrier and we just have a slit here, the wave will continue to go through. But what happens to a wave when it comes to a barrier? It wants to bend around the barrier, right? So if we just focus on this wave, this black represents the barrier and it filters out that part, but this wave goes on through. And this point here goes through, but it's going to diffract around this edge and diffract around this edge. And so it will form waves that go like this. Well, so will this slit, which, just to make things a little more clear, I'm going to use a different color. It is the same wave, but I'm going to go to blue here. And this wave will come out and do something like this. And everywhere a blue and a red line cross, that would be a crest. That would be a amplification or an constructive interference. And so my drawing's not perfect, but if we connect those dots, we could draw lines where these points intersect, and those would be where we get the constructive interference. And what happens where the blue and the red don't meet? We would get destructive interference. So we would get nothing. We would get nothing at these points. Well, if we were to if we have these rays constructively and destructively interfering, and we put a screen that these light rays can shine upon, we're going to get bright spots at these locations and we will get dark spots in between. So it'll get darker and darker. Now, it's kind of interesting that we don't get them separated quite like this. It's really bright, and then it gets dim, kind of like that. So we get bright, dark, whoops. And so there's a definite intensity of the brightness near the middle, and then it wears off. Why? Because here we get complete destructive, here we get complete constructive, and in between we get constructive and less constructive until it's completely destructive. So you get this blurring of the bright spots and dark spots. So it's not clean cut in between them. And so there's sort of a blurring that goes on between. And another way I try to illustrate this is that if you were to start, I use my arms here, from here to here, they'll be the same length if I come from the same points going to the same distance from each other. And if we shift a little bit to the right or to the left, if we shift far enough, we can be one whole wavelength out of phase, or back into phase. Whereas if we do only half as much, we will be half a wavelength out of phase. So when we're in phase, constructive interference, start to move this way, we get half a wavelength out. Now we're going to have destructive interference. Go a little farther, and we will have, again, constructive interference because we're one whole phase out of phase, and so we're back into phase. So in the center one, we're going to get that brightest spot. And as we go further away, you get to be sort of half out of phase, and you get a dark spot. And you keep on going, you get a whole wavelength back into phase, and we get a bright spot. So you can see some of these diagrams in your book. In our book, the diagram here demonstrates what we just looked at, where if we have two wavelengths coming to meet and they're in phase, like when my hands are put together, then we're going to get a bright spot. If we move them such that they're completely one wavelength out of phase, then we'll get another bright spot. But if we are half a wavelength out, we will get destructive interference, and we'll get a dark spot. So this wouldn't be any fun if we couldn't do any calculations with it. So let's take a look at this. So if the difference of the distance traveled by two waves is called the difference in distance traveled by two waves is called their path difference. So here we have two slits magnified in a screen, just like what I showed you earlier. There's two slits, and they're not very far apart. The distance between the slits is called d. Now, the path difference is equal to d sine theta. That's this distance times this angle. Why? Because this would be the sine of this triangle. And so if we wanted to find the path difference, we would just simply need to know the distance between the two slits and the angle, and we could figure out this length. Well, if this length matches the wavelength, why, it's going to be a bright spot. If it doesn't match the wavelength, it's going to be a dark spot because they're not in phase as they keep on going. So if the path difference is 0, that means they started both the same place and they ended the same place, like in our case over here. We're going to get a bright spot. So the d sine theta, if they're both going to the same point, would be 0. And that is called the zeroth order maximum, or the central maximum. And that's when m is equal to 0. The path difference is 0. The next spot, which would be exampled by this one, would be here's center, to the left of center, to the right of center, up and down. It wouldn't be at the center. That would be the first order maximum, or m equal to 1. And we can keep on going, 2, 3, 4, and so on. Now, what if we're half a wavelength out of phase? Well, then we're going to get a dark spot. So how do we do a calculation for that? Well, we use the same equation, but to get a complete dark spot, we would have to be a half a wavelength out of phase. So whatever is in phase, we would just simply have to add half a wavelength to it. So for our first one, well, m equals 0, we would go a half a wavelength out of phase, and we would get a dark spot. So 0 plus 1/2 would be 1/2. If we wanted to pass the first bright spot, you'd add 1 plus 1/2, and you get the next bright or dark spot. On the next page, we find a diagram showing two slits and light coming through those two slits. If they were to meet in the middle, that's where our bright spot is. And then we can continue to have bright spots on either side. You'll notice that there's M there, there's theta, and this is the viewing screen, much like I showed you at the beginning of the video clip with the red dots. Now, the bright spots in plural form of maximum is maxima. And the dark spots, since there are many, the plural of minimum is minima. And using this method was actually one of the first ways that light wavelength was actually calculated. So we can use that equation and we can do our algebra and we can actually figure out what the wavelength is of a particular color of light using this method. So what will follow here, I will show you a picture of the answers, or I'll show it to you here. There are the answers. Here are the answers. This crossed out number is correct, 25.2, and these are the answers for the top part of the page, and then the answers for the bottom part of the page are down there. That's it for now.